Question 9 from Section 1 of the 2017 Higher Physics Examination. Radiation is incident on a clean zinc plate, causing photoelectrons to be emitted. The source of radiation is replaced with one emitting radiation of a higher frequency. The irradiance of the radiation is incident on the plate remains unchanged. Which row in the table below shows the effect of this change on the maximum kinetic energy of a photoelectron and the number of photoelectrons emitted per second from the metal? So we start off with the equation which gives you the maximum kinetic energy of an ejected photoelectron, EK, and it's equal to the energy of the incoming photon, HF, take away HF naught, and HF naught is the work function. It's the minimum amount of energy needed by the photon in order for the photoelectron to be ejected from the surface. Now we're actually increasing the frequency of the incoming radiation, so this means that that's going to get bigger. HF is going to become bigger, so the energy of the photon is going to become bigger. HF naught, which is the work function, well, that stays the same because we're dealing with the same metal. So that means that the maximum kinetic energy, EK, that's going to get bigger. So right away we know the answer to the first column. The maximum kinetic energy of the photoelectron will in fact increase because you're using photons of a higher frequency, which means they're coming in with a higher energy. Now it's the second column which is a bit of a problem because we have to really delve into what's happening with this irradiance. The irradiance really is the power or the amount of energy per second arriving on a certain area of a surface. But before we get into that, we want to take you to another diagram which is going to show us an analogy of what's really happening. And here's a diagram here. Now, if we've got two identical jugs and we want to fill them to the exact same volume and we've got to be dropping water into those jugs, then it can be seen that the one where we drop in the small drops, we're going to take a lot more of those small drops to put the volume up to that certain level. If we fill the jug with larger drops, it's going to take fewer, and that's common sense because the bigger the volume of the drop, the fewer it needs to fill up the jug. Small volume drops, you need a lot more of them to fill the jug up to that same level. So it's going to take a fewer large volume drops than small volume drops to fill the jug. Now let's keep that in our minds and go to the picture of the photoelectric effect and what is happening. And this is what's happening here. We have a ray of light coming in which contains photons, and these photons carry a certain energy with them, HF, and they will deposit that energy onto that plate, onto a certain area of the plates, and that's going to be called the irradiance. The irradiance is the amount of energy per second arriving on a unit square of material. Now if you look very closely at this, if we have low energy photons, small drops, it's going to take a lot more of them to provide the same energy deposited on the plate. But if we have high energy photons, that's the same as the large drops, then we're going to need fewer of them. So it's going to take fewer high energy photons to deliver the energy E to that plate or that area compared to the low energy photons, which is going to take a lot more. So the very fact that we have increased the frequency of the light means that we're providing now more of high energy photons. And high energy photons, to provide the same irradiance, you require less of them. So if you require less of them, you're going to get less photoelectrons actually ejected from the plate. So a proper answer for the question is going to be decreasing. The number of photoelectrons emitted per second is going to decrease. So our answer to that is going to be D. Now it's not, in fact, pretty obvious, that one. I think we can get the first part of it using the maximum kinetic energy formula. It's the number of photoelectrons emitted per second which causes the problem. And to help us with a bit extra studying this one, I'm going to show you the following simulation. So here's the simulation. We have the photoelectric effect simulation on the left, and on the right we have the data which we'll be examining in this experiment. Now we see the photoelectric effect consists of a source of light represented by a torch shining on one of the metal plates called the cathode, which is made up of the element cesium. So it's the metal cesium which is on that metal plate, the cathode. At the far end you have the anode, and connecting the anode you have a voltmeter which really is registering the potential difference across this, but we're not really going to measure the potential difference because we're not attaching a battery to it as such. So therefore on that right hand panel U is going to equal to 0. That's the potential difference across the plates. We're not going to have a potential difference, but we're going to measure a current, and that's measured by the microammeter, which is that meter on the right there. Now on the data we can see first of all at the top the metal is cesium, the wavelength of the incident light is 550 nanometers, and the irradiance, which is very important, so we want to keep that constant, is 5 watts per meter squared. That means that the amount of light on that metal plate amounts to 5 joules per second every meter squared of that metal plate. I'm going to keep that constant. As I said before, the potential difference across the metal plates is 0, no battery, and the 4 figures below give us indication of the main parts of the data. W stands for the work function of the metal. That's not going to change. E photon, the one below it, that is the value of 1 photon's energy of light from this light of wavelength 550 nanometers. EK is the maximum kinetic energy of the emitted photoelectron, and you can see the photoelectrons are being emitted from the metal plate because the energy of the incoming photon is going to be bigger than the work function, so if you're going to get an excess amount of energy. And the most important figure we're looking at is I anode, 1.11 times 10 to the minus 3 amps, and that's going to give us a measure of how many photoelectrons are reaching that plate, which in turn equals the number of photons which arrived in the plate to begin with to release those photoelectrons. So that I anode really represents the number of photons which are striking that plate. Now the question says we have to increase the energy of the beam of light, and we've got to keep the radiance constant. So what I do is I'm going to increase the energy of the incoming photons by reducing the wavelength, because if I reduce the wavelength I'm increasing the frequency of the light, and if you increase the frequency of light the energy of the photon is going to increase. So if I just decrease the wavelength, I'll take it down to about 350. There it is there, 350, and you can see from the simulation that as I've increased the frequency of the incoming light, definitely the photoelectrons are moving faster, which means they've got a bigger kinetic energy, therefore a bigger maximum kinetic energy. So that's one of our answers there. But do you notice that we've got less photoelectrons coming off? And that's backed up by our I anode currents, 7.06 times 10 to minus 4 amps. So we've really reduced the amount of photoelectrons coming off, which in turn tells us that we've had a reduction in the photons produced by this light, and that's because we have to keep the radiance the same. The radiance is kept constant. Now the radiance is kept constant, the amount of energy deposited on the metal plate. You think back to the drop experiment. If you've got tiny drops, you need a lot more of them to make up a certain volume compared to bigger drops. If you use bigger drops, you'll need fewer of those bigger drops to make up a certain volume. Well, it's the same with the energy E. If we want a certain amount of energy E to be landing on that metal plate, if we're going to use photons of high frequency, which means big lumps of energy, we're going to need fewer of them. And if we have fewer photons striking the plate, we're going to get fewer photoelectrons emitted, and that's what we're seeing there right now. So that's a very good simulation to play about with and to get those ideas into your head. Question 10 from section 1 of the 2017 Higher Physics examination. Ultraviolet radiation of frequency 7.70 times 10 to the power 14 Hz is incident on the surface of a metal. Photoelectrons are emitted from the surface of the metal. The maximum kinetic energy of an emitted photoelectron is 2.67 times 10 to minus 19 joules. And we're asked to find the work function of the metal, and we're given those 5 choices. Well, we look up our data book and we can find the equation giving us the maximum kinetic energy. It is EK, that represents the maximum kinetic energy of the photoelectron emitted, and that's going to equal to HF, which is the energy of the incoming photon which lands in the metal, and we have to subtract from that the work function HF naught. Remember, HF naught, the work function, means the amount of energy, the minimum amount of energy a photon must have in order to eject an electron from the surface of the metal. Now we're asked to find HF naught, so we have to do a wee little bit of algebra here. So we add HF naught onto both sides, so we get EK plus HF naught, and that's going to equal to HF. We want HF naught on its own, so we have to subtract EK from both sides, and we're left with HF naught, the work function, is going to equal to the energy of the photon HF, and we subtract from that the maximum kinetic energy of the photoelectron. So that's our equation set up. All we have to do is plug in the numbers. So we have HF naught, which is the work function, and that's going to equal to HF. So in order to find HF, we have to find first of all Planck's constant, and Planck's constant, as you can see from the table there, is H equal to 6.63 times 10 to minus 34. So that's the value for the constant. I'll just dip that down there so you still can see it. So all we have to do is plug that number into our equation. H, put a bracket down here, H is going to be 6.63 Planck's constant times 10 to minus 34, and we're going to be multiplying that by the frequency of the light, which we're told is 7.70, so we'll multiply by 7.70 times 10 to the power 14, and we have to take away the maximum kinetic energy of the photoelectron, emitted one, and that's 2.67 times 10 to the minus 19 joules. So there's our equation all set up with the numbers in it, and all we have to do is do our calculator work, and we end up with the work function HF naught turns out to be the order of 2.435 times 10, and it's to the minus 19 joules. We can round that up to 2 significant figures, so the work function HF naught is equal to 2.44, that's 3 significant figures, sorry, times 10 to minus 19 joules, and that means our answer is going to be 2.44 times 10 minus 19 joules is going to be B. So our answer for question 10 is going to be B. Question 11 from section 1 of the 2017 Higher Physics Examination. A student makes the following statements about waves from coherent sources. 1. Waves from coherent sources have the same velocity. 2. Waves from coherent sources have the same wavelength. And 3. Waves from coherent sources have the constant phase relationship. And you're asked to say which one of these statements are correct. Well, in fact, all of them are correct, because coherent sources will emit waves with the same velocity, coherent sources will emit waves with the same wavelength, and coherent sources will have a constant phase relationship. So the answer is going to be E, which means all three, 1, 2 and 3. But it's a little bit extra study. Let's look and see what in fact constitutes coherent waves by looking at this simulation. So here's a simulation of coherent waves. We have a red wave and a blue wave, and they are coherent. They're coherent because they have got the same wavelength, the same amplitude, and they're travelling at the same speed. If they're the same wavelength and same speed, they'll have the same frequency. And what's more, they've got the same constant phase difference between the blue and red waves. Where do we see the phase difference? Well, if you look closer between the peaks of the red and blue, you can see the distance between the red and the blue waves is always the same. That means that there's going to be the same time difference between the blue and the red. So if you watch the two waves pass the centre zero line here, you can see blue, red, blue, red, blue, red. They always pass with the same time difference and the same little distance between them. That means that they are in constant phase difference. And that means these two waves are what we call coherent waves. So here we have two incoherent waves. We've got a red one and a blue one. And as you can see, the wavelength of these waves are exactly the same, but their speed is different. And if their speed is different, it must mean that their frequency is different, so they're not coherent. And one other thing which adds to the incoherence is that the phase difference is constantly changing. And you can think of that as the distance between the peaks is constantly changing. Now you can see them way apart from each other, they're coming closer to each other, saying bang on each other, and then of course they're away from each other again. So that means they're going to have a varying phase difference, and if you get a varying phase difference, you really are an incoherent wave.